This is the third segment on topic 2.3. Now we're going to talk a little bit more closely about the relationship between work and energy. And we've seen in the previous two segments that you can't really talk about one without the other. Work is the transfer of energy. Energy is the ability to do work. If we think about this a little bit more closely, this is actually addressed in what's called the work kinetic energy theorem. And so a couple things that we've talked about that we should know by now. When we have some object and we exert a force on it, we have some net force, that object is going to accelerate. It's either going to speed up or it's going to change directions. If the initial velocity of that object was u, then after some displacement, after that force has been exerted over some distance, it has some new velocity v. So if we express this mathematically, and this is one of our 5 key kinematics equations, final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement over which that acceleration occurred. Remember from Newton's second law that force is equal to mass times acceleration. If we rearrange that a little bit, acceleration is then equal to force over mass. Well, we can take this, plug it in for acceleration, and we get v squared equals u squared plus 2 times force divided by mass times the displacement. If we isolate a little bit, let's subtract u squared from both sides, and we get v squared minus u squared equals 2fs over m. Easy enough. Let's multiply both sides by m and divide both sides by 2. So we're going to multiply both sides by m and we're going to divide both sides by 2. So over here on the left, our masses will cancel out, as will our 2's. On the right, we're going to distribute our mass through and our 2's. So we're going to get mv squared over 2 minus mu squared over 2, which if we rewrite that, we get, and notice that we're changing s to x, not a big deal, it's just the displacement still, but fx equals 1/2 mv squared minus 1/2 mu squared. This is important because fx will maybe recognize from fd, which is equal to work. Right here, 1/2 mv squared, v squared is equal to the kinetic energy of an object. And so 1/2 mv squared, this is our final kinetic energy. 1/2 mu squared, this is our initial kinetic energy. And so on the left you have the work done on the object. On the right you have the total change in the kinetic energy. And so what this is telling us then is that the work done on an object is equal to the change in that object's kinetic energy. And again, this is what we just mentioned, that kinetic energy, or E sub k, is 1/2 mv squared. And so when we do work on an object, we change its kinetic energy. Now this also then leads us to one of our conservation laws, and we talked about conservation of momentum. Now we're going to talk about conservation of energy. The energy of a system, the energy in a system, can neither be created nor destroyed. It only changes forms. So the energy at the beginning is always going to be equal to the energy at the end. Now, we have to be careful when we're talking about this. And it depends on what we're talking about when we talk about conservation of energy. Energy changes form. So if you slide a book across the ground, you look at it, it appears to slow down and stop and lose energy. But what's really happening is there's a force of friction that's being exerted on the book to convert mechanical energy, the energy of that book moving, into thermal energy, which is heat, which is energy in the molecules. And so if we're talking about mechanical energy is not necessarily always conserved. If there's friction, which in real life there always is, mechanical energy is not conserved. But the overall energy of the system is. It's just a matter of what happens to that energy and where it goes. If you really want to get technical, energy can be generated through the conversion of mass to energy and lost through the opposite reaction, but that's not something that we're going to address at this point. When it gets down to it, really, it's the conservation of mass energy. Now, to go along with what we just said, in the absence of friction, the total mechanical energy of a system is conserved, and that absence of friction is key. So what that means is that in the absence of friction, the total potential plus kinetic energy at the beginning is equal to the total potential plus kinetic at the end. If we're just talking about gravitational potential energy, we can expand on that a little bit more and say mgh initial plus 1/2 mu squared is equal to mgh final plus 1/2 mv squared. And so this gives us another tool to approach some of our previous problems that we've addressed, particularly with objects in free fall or objects moving up and down hills, and we'll get into some of those a little bit more later on. Now, if there is a frictional force or some other resistive force, such as air resistance, then mechanical energy is not conserved. These forces, as I mentioned earlier, convert mechanical energy into thermal energy. But it's important to understand that even though the energy changes forms, it's not truly lost. It's just in a form that we don't see. And it's not just mechanical to thermal that's going on around us. Conservation of energy or conversions of energy, rather, are happening all the time. Whether it's from electrical to radiant and heat in a light bulb, or whether it's chemical to mechanical in a car engine, or nuclear to thermal when we're in a nuclear power plant, or chemical to thermal to electrical in a coal-fired power plant or a fossil fuel-fired power plant. These conversions of energy are going on all around us all the time. In your body, you're converting chemical energy from the food into thermal energy to keep your body warm. You're converting it into mechanical energy as you move around and write and do all the things that you do on a daily basis. And we can look at these systems and we can follow the energy through. And for us, our energy really has its source at the sun in the form of electromagnetic or radiant energy. And then from there are numerous pathways that it follows as it gets to us and then passes out from us. And then one other type of energy that I just want to address real quickly, because we'll see it here and there, is elastic energy. And elastic energy is the type of energy that's in springs, it's in rubber bands, things like that. And the unique thing about the elastic force and elastic energy is that the elastic force is equal to negative kx. And so what this tells us is the force is proportional to the displacement. And you've seen this anytime you've tried to stretch a rubber band or compress a spring or something like that. As you stretch it further and further, it gets harder to continue stretching it. And the elastic energy also increases as we continue to stretch it. And so the elastic energy equation is similar to our kinetic energy equation, except instead of m and v, we have k, which is the spring constant, which, as we talked about when we talked about elastic force, is unique for any individual object, spring, rubber band, whatever it happens to be, and x is the displacement. It's the distance it's stretched from equilibrium. Okay, not the total length of the spring, but the distance stretched or compressed from equilibrium. And so with those relationships, now we can address some of the problems that we've seen previously in a different light.